Well, good evening, everybody. Zhaozhi Qian is one of our award winners. We have getting on for 200 applications for these prestigious awards. And Zhaozhi is going to talk to us about new work he's doing, but which draws on his award-winning activities about the longitudinal study of the impact of treatment. So if you're there, Zhaozhi, off you go, please.
Yeah, thanks. Thanks for inviting me. Let me share screen. Yes. Hello, everyone. I'm Zhaozhi. I'm delighted to present my work on SyncTwin, which is a method tailored for estimating treatment effect with longitudinal outcomes. This work is jointly done with my collaborators, Yao Zhang, Ivana Bika, Angela Wood, and my supervisor, Mihaela Vandashar. The general problem we consider in this work is ITE estimation, or estimating the causal treatment effect from observational data. So this problem setting is different from the conventional randomized controlled trial setting, where the treatment is randomized and allocated in a unconfounded fashion. So the challenge we have in this work is that observational data contains so-called confounding bias, and we need a proper method to adjust for these biases. The specific scenario we consider is the so-called LEAP setting, which stands for longitudinal, irregular, and the point treatment. So as it is illustrated in this figure, the outcomes of interest are observed over time, before and after the treatment. And there also involves a set of covariates that are also observed over time, and these covariates may influence the treatment allocation as well as the outcome. And finally, we consider a treatment which is also allocated at some fixed time point and stay fixed during the study. So observational studies is important because it complements the traditional clinical trials. Clinical trials are very expensive, time-consuming, and may underrepresent the population. However, when the drug is on the market, there's a standard post-marketing surveillance program which collects the real data of the drug usage and clinical outcome. And by analyzing these observational data, we can have a better estimate about the drug effect and on the performance on different subpopulations. And this is the main motivation for this work. The specific LEAP setting we consider is also very important for medical problems because it captures the characteristics of the electronic health records data. The patient's health status are measured longitudinally at irregular intervals. Furthermore, the treatment effect on clinical outcomes may be time varying, and it is important to understand the effect over different time horizons. For instance, maybe the drug is performing very well at the beginning, but later the patient develops drug resistance. And finally, the point treatment scenario is also widely applicable. Very often the allocation is fixed within the treatment regime, which can be weeks or even years. This setting also captures one-off treatments such as surgical interventions or transplants. However, the current method tailored for the LEAP setting is currently underdeveloped. Most works consider the static setting, which does not involve any temporal aspect. Some works address the more challenging dynamic treatment setting, where the treatment allocation can change during the study. There's another literature called synthetic control, which addresses the LEAP setting, but it makes some unrealistic assumption on the data generating process. So the key insight of this new method is to fully leverage the pre-treatment outcomes. These outcomes are before the treatment and are influenced by the treatment. However, they may give information about the counterfactual outcomes due to the temporal structure that is inherent in the time series. Unlike existing methods which ignores pre-treatment outcomes or treat them as temporal features, SyncTwin explicitly models the outcome time series. And as we'll show later, this can improve the estimation accuracy as well as bringing additional benefits. So there are two important additional advantages of the newly developed SyncTwin method. First of all, SyncTwin enables individualized error control. This means that for each target individual, it can inform the user whether to trust the estimate or not. Understanding the failure cases of the model is crucial for mission-critical applications such as healthcare. When a reliable estimation cannot be made, the user of SyncTwin can be alerted and fall back to expert judgment. And one typical reason for not being able to reliably estimate treatment effect is that this certain individual is an outlier and is different from the training population. And the second benefit is that SyncTwin also enables explainability by example. This means that it can explain the estimate of a target individual based on a small subset of contributors. These contributors are deemed similar to the target. So the user can examine these contributors to fully understand and reason about the estimate. This is in contrast with other machine learning or AI models, which are often black boxes and not understandable by human experts. SyncTwin consists of 3 steps: encode, synthesize, and estimate. In the encoding step, the neural network encoder translates the longitudinal covariates before treatment into a representation vector. The representation is learned to satisfy 2 requirements. First, it can predict the outcomes with a linear model. And secondly, it can reconstruct the covariates with a suitable decoder. SyncTwin is agnostic to the exact encoder architecture, but we found that RNN with attention to perform very well in the experiments. In the second step, we select and weight individuals from the control group such that the convex combination of these contributors match the target individual in the representation space. In other words, the synthetic twin representation is the weighted average of contributors to the representation. And these weights are found by solving this convex optimization problem shown here. And in the final estimation step, the same set of the weights that we found in the last step are applied to the outcomes before and after treatment. In other words, our final estimate is a weighted average of the contributor outcomes as shown in this equation. Note that we can estimate the outcomes both before and after the treatment. And the outcome difference after the treatment gives the estimate of the treatment effect. And the difference before the treatment can be used to compute the individualized error, as we'll discuss later. SyncTwin relies on the standard assumptions in causal inference, such as consistency and no anticipation. We also assume that outcomes are generated by a latent factor model, as shown in this equation. The latent factor model assumption is not too restrictive in practice because the latent factors can relate to the covariates in a complex and nonlinear way. And furthermore, these factor model assumptions are also used in literature very widely, such as econometrics. And we show formally that under these assumptions, the error in the pretreatment outcomes can be used to bound the error on the counterfactual outcomes. This provides a way to control the error on the individualized level and enables individualized error control, as I alluded to before. In addition to extensive simulation study, we performed a real data study to see if SyncTwin is able to reproduce the findings of a large-scale randomized controlled trials. So clinical trials are the gold standard for causal inference, and the trial we consider is the protection study, and it is the statins cholesterol lowering effects. The trial reports that the cholesterol will have the effect of minus 1.26 millimole per liter in the first year of follow-up. And we apply SyncTwin to a cohort that is comparable in the randomized controlled trial, but it is selected from an observational data, from an observational electronic health records. Since SyncTwin is applied to an observational data set, it contains confounding bias due to non-randomized treatment allocation. However, we found that the method produces a very similar treatment effect estimate from the trial, but other baseline models failed. And here I would like to point out that we compare the average treatment effect because this is the number reported in the randomized trial, but SyncTwin can actually do better and produce an estimate on the individualized level. So if you're interested in further details, please check these papers and check out the links below. Thank you. That's all of my presentation.
Zhaozhi, thank you very much indeed. Fascinating, and presumably this, I don't see any questions up, so I'll abuse my position and ask one if I may. Is this approach now in use in real time, as it were? Is it still experimental, or are people using it for real in routine medical work?
So the treatment effect estimation method is an innovation on the methodological level, and it might take time to be really applied. So currently we are working on validating it on more clinical trials. So the next step is to, because we already replicated one large-scale clinical trials, the reasonable next thing to do is to try to replicate more clinical trials and to have a better understanding about the robustness of the method and the various challenging conditions. And after that, we want to do some real study to find out where the opportunities is. So for instance, we identified a scenario, for instance, that in many cases, the randomized controlled trials are excluding people with, for example, comorbidities, such as diabetes or the elderly population. However, for drugs like statins, they are routinely prescribed to people with comorbidity and people are relatively older. However, since there is a missing information, since these people are not recruited to the clinical trial, the treatment effect on this subpopulation is currently unknown. So we hope to use this the SyncTwin method to estimate the treatment effect for those underrepresented population in the trial.
Excellent. And clearly this approach means that clinical trials be conducted more quickly and more accurately, which has to be a wonderful thing, given that it looks as though we're going to need more medication approved more quickly than we have been able to do hitherto. So thank you for that. Fascinating.